highest amount of cubes. And now the blue dashed line is the upper bound when I allow these two base stations to cooperate in an unlimited fashion. It's basically I have a cycle system because I assume that these two base stations they can cooperate in an unlimited fashion, so they can exchange information in arbitrary way, and that gives me the upper bound of the blue dashed line.
So you can achieve a lot of the
difference capacity because you can use these two receive antennas.
if they code together.
Yes. I can do joint code.
Joint.
Yes, and I can have a beacon from that. Yes.
To research.
Yes.
So tails up as the INR goes up.
Yes, because now I have a stronger channel from the other because for user one, right, you have a stronger path from the transmitter to the second base stations. The second stations can have this stronger signal and convey this stronger signal perfectly to the first base station. And then they can decode jointly, and then you can have a beacon.
What is in here is not really power control. In terms of, because what happens on the right-hand side, why does the blue curve go up? It's actually the transmitted power increases. And it's because as the INR is 20 dB, you can actually have more.
Yeah, actually, you have more power.
There's only cases that this
Yeah.
As you're seeing, it can be effective interference is lower.
The interference.
Collaboration techniques.
The difference is no longer 30 degrees.
What's happening up there, to make it very simple, is these guys are the negligible links, and these guys are the strong links. And as I crank up my interference to noise ratio even further, I actually crank up the power. So I'm not limiting this to something, but I'm actually cranking up the power. And these guys are basically turned off out here. When you say so? Going up.
That would be after
To the right of that.
Yeah,
To the right.
let's you go to the right there.
Exactly. Right there, where we have a 3 dB gain.
So at the rightmost of this figure is when INR is 20 dB, which is the same as SNR, which is when the cross link is the same as the direct link. At that point, I can use maximum ratio combining among these space stations, and then I can get a power gain. So that's why I have a boost up at the end of the video. And as Gerhard mentioned, as I increase the INR to infinity, that's the case where the
Just
direct
goes
link
linear.
Yeah, that's right. So our contribution is we characterize the blue solid curve, which is the achievable rate with the limited amount of receiver cooperation, where the receiver cooperation is receivers are cooperating at rate 2 bits per second per hertz, which is a finite number. And you can see that even in this at this limiting rate, you can have some cooperation gain. You can have some gain from this cooperation. That's kind of an evidence to motivate that.
What is the limiting factor for cooperation rate? What is it that's limiting your cooperation rate mainly?
It's mainly because because the backhaul is built up there and it's fixed, right?
Yeah.
But it's not scaled with the for example the frequency, the bandwidth, right? So imagine in the future zero networks you can have larger and larger bandwidth.
So you
support more and more users.
You're assuming a limited bandwidth on the backhaul.
Yes, because
Okay, so you're not assuming you've got a huge pipe.
Yeah. Because you have a huge pipe, I can just simply quantize my resistance very finely, and then I can convey
So
almost
it's really resource limited as opposed to technology limited, something like that.
Yeah, because maybe this backhaul is a resource that is going to be shared by all the users within the cell, right? And that can be managed in the future because we may support more and more users. Because we may not want to put cell towers within an area. Right? So each cell tower can support a lot of users.
This is a wireless backhaul or wired?
Doesn't matter.
It doesn't matter.
It does matter because this assumes zero delay.
I assume that
If you timestamp, you can decode later. Right? So,
yeah,
You could do that.
yeah.
so why 2 bits per second? Or do you try different numbers or you do different version?
Bits per different
The
numbers.
cooperation rate? You're trying 2 bits per second.
Yeah, so this is the only example.
Just an
yeah, I have an example for 4 bits per second.
Okay. Oh, okay.
So,
Okay.
so that can show you there's an increase. So this is just a showcase that I do have some gain from even from limited receive cooperation. That gain is pretty much significant. Okay, so the goal of my this is, as I said, this is a little bit from my qualified exams, so I have to propose some goals for my PhD study. So my goal is to build up some cooperative interference management schemes on current zero networks, so current or forthcoming zero networks, okay, like the WiMAX or LTE, for example. And so I consider these kind of zero networks with backhaul cooperation among base stations. So to build up these cooperative interference management schemes, there's a lot of aspects that I have to look into. For example, what is the cooperative strategies among base stations with these backhauls? And how should we change our coding schemes on the base stations and modules to adapt these cooperation strategies correspondingly? So I have to look at the coding strategies as well. So this is like the physical layer issues, right? And also in the MAC layer, we have some other issues. For example, now that these backhauls, they are some kind of scarce resource in my formulation, or in various scenarios. So there's a resource allocation problem because I can assume that different pair of users are using different amount of backhaul for them to cooperate and mitigate interference. So how should we allocate these backhaul capacities to these users so that I can achieve the optimal aggregate throughput? And also, because I cannot, in practice, you have these synchronization issues among base stations, so you cannot assume that all the base stations they can cooperate in a global fashion. So how do we cluster these base stations so that in a reasonable way, so that I can still get a good performance using this cooperation to mitigate interference. And finally, it turns out that from the information theory study, we would need channel state information and the transmitters if we want to get significant gain in the spectral efficacy.
What's transmitted?
The channel state information and the transmitter. So how do I get the downlink channel state information and transmitters, and how do I get uplink channel state information and transmitters? And it turns out that you can use this very simple scheme too.
But then the uplink is not a big deal. Is it? You don't really need it.
It turns out that if I want to, so the coding speed itself will require channel state information.
To choose the right MCS or what?
Basically, I need the significant thing is that I need the channel strength from the crosslink. So I would want to have some estimate of what's the interference coming from. What's the interference? What's the channel strength from the interference transmitter?
Yeah, but that's only exactly. That's only channel strength, which is not that big of a deal because that is symmetric.